We've spent centuries looking for another Earth, scanning the darkness between stars, building telescopes that peer deeper into the cosmic night, searching for that pale blue dot, that familiar silhouette of continents and oceans, that mirror image of home. But what if we've been searching for the wrong thing? What if Earth isn't the template for life in the universe, but the outlier? It's a humbling thought, almost offensive in a way. We like to think of our world as special, and it is. Earth gave birth to us, to consciousness itself, to beings capable of asking these questions. But being special doesn't mean being optimal. Being unique doesn't mean being ideal. There's a concept that's been quietly growing in the minds of astrobiologists over the past 2 decades. A possibility that challenges everything we assumed about where life could thrive. They call it superhabitability. The idea is simple, almost too simple. There may be worlds out there where life doesn't just survive, but flourishes more easily than it does here. Planets warmer than ours, wetter than ours, more stable than ours. Places where the conditions that make life possible aren't delicate accidents, but robust certainties. Think about Earth for a moment. Really think about it. Yes, we have liquid water. Yes, we orbit at a comfortable distance from our star. Yes, we have an atmosphere that shields us from radiation while letting sunlight through. But we also teeter on the edge of ice ages. Our magnetic field flickers and threatens to reverse. Our continents crash together and tear apart in cycles of destruction. Mass extinctions punctuate our history like ellipses in a sentence that keeps getting interrupted. We made it. Life made it. But it was never easy. So, what would easy look like? Let's start with something fundamental. Mass. Not the mass of a star or a galaxy, but the mass of the planet itself. The amount of rock and metal and matter gathered together in one place, pulling inward with gravity, holding everything down. Earth weighs in at roughly 6 trillion kilograms. We call that one Earth mass, because we do love to measure the universe against ourselves. But what if one Earth mass isn't the sweet spot? What if there's a better number? Planetary scientists have run the calculations. They've built models of how worlds evolve, how they hold on to their atmospheres, how their interiors churn and their surfaces reshape themselves. And the numbers they keep coming back to are intriguing. 1.5 to 2 Earth masses. That's the range. That's where theory suggests habitability might peak. Not too small, not too large, just right. But why? It comes down to what's happening deep beneath the surface, inside a planet. In that hidden realm of molten rock and flowing metal, there's a kind of slow-motion dance taking place. We call it plate tectonics. The crust breaks into massive slabs that slide over and under each other, diving back into the mantle, rising, all again as new seafloor, colliding to build mountains. This process does something extraordinary. It regulates climate. When carbon dioxide builds up in the atmosphere, rain pulls it down into the oceans. It reacts with rocks, forms carbonates, gets carried down into the mantle at subduction zones. Volcanoes release some of it back. It's a thermostat, a planetary feedback loop that's kept Earth habitable for billions of years, despite the sun growing steadily brighter. But there's a catch. Plate tectonics requires heat from below. It needs a molten interior, a churning engine that won't quit. And Earth's engine is running down. Our core is cooling. Our magnetic field is weakening. In another billion years, perhaps less, the plates might stop moving. The thermostat might break. A larger world, though. A world with more mass. That world has more gravitational energy locked inside it, more heat to release, more radioactive elements decaying in its depths, keeping the fires burning. Its plate tectonics could run longer, much longer, 2 billion years longer perhaps, maybe more. That's 2 billion additional years for life to evolve, to diversify, to experiment with forms and functions we can't imagine. 2 billion years of stable climate, of continents drifting and reshaping, of ecological niches opening and closing in an endless creative ferment. That's where superhabitability begins to make sense, in deep time, in the long game of evolution. But here's where theory meets reality, and reality gets complicated. There's a world we've found, a world that sits in our telescopic catalogs with a designation that sounds more like a serial number than a place. Gliese 667 cc. It orbits a red dwarf star 22 light-years away in the constellation Scorpius, and its mass, roughly 4 times that of Earth. 4 Earth masses. That puts it outside the theoretical sweet spot, beyond the range where superhabitability is supposed to peak, but it also sits squarely in its star's habitable zone, that band of orbital distance where temperatures allow liquid water. So, what is it? Is it a rocky super-Earth with towering mountains and vast oceans and continents that will stay geologically active for tens of billions of years? Or is it something else entirely? This is where the paradox deepens. This is where hope and doubt begin their delicate dance. Because mass determines more than just how long a planet stays active. Mass determines what kind of world it becomes in the first place. Gravity doesn't just hold rocks together, it holds gases. It grips molecules of nitrogen and oxygen and carbon dioxide and prevents them from escaping into space. The more mass a planet has, the easier it is to retain an atmosphere, to keep that precious blanket of air wrapped around its surface. For a world in the superhabitable range, 1.5 to 2 Earth masses, this is a gift. These planets can hold on to thicker atmospheres than Earth. They can weather solar storms without bleeding away their air. They have staying power. But there's a threshold, a point where more mass stops being helpful and starts becoming dangerous. Somewhere around 5 to 10 Earth masses, something changes. The planet's gravity becomes strong enough to capture not just the heavy gases that make up breathable air, but the light ones too. Hydrogen, helium, the primordial gases left over from the planet's formation, the same gases that build gas giants. At that mass, you don't get a superhabitable world. You get a mini Neptune, a planet drowned beneath a crushing envelope of hydrogen and helium thousands of kilometers deep. No solid surface, no oceans of liquid water, just an endless fall into thickening atmosphere until pressure and temperature rise so high that gas becomes liquid, becomes exotic phases of matter that don't even have names. These are not worlds where life as we know it can exist. And Gliese 667 cc at 4 Earth masses sits uncomfortably close to that transition. Not safely in the superhabitable zone, not obviously in the mini Neptune category either, right on the edge, right where uncertainty lives. Did it form rocky and hold a reasonable atmosphere? Or did it accumulate too much hydrogen in its youth, swelling into a drowned world beneath skies that would crush any creature we can imagine? We don't know yet. We can't see it clearly enough. All we have is its mass, its orbit, and the calculations that spiral out from those numbers into possibility space. It invites both hope and doubt. It reminds us that the universe doesn't hand us easy answers. But let's step back. Let's remember what we're really talking about. Mass alone doesn't make a world habitable. It never could. A planet isn't a single variable in an equation. It's not a data point on a graph. It's a system, a churning, evolving, breathing system of rock and water and air and energy. Habitability isn't a single number, it's a symphony. Mass is one instrument. It sets the tempo, determines how long the song will play, influences how loudly the other instruments can sound. But a symphony needs more than rhythm. It needs melody, harmony, dynamics that shift and surprise. And the next instrument, the one that shapes everything else, the one that bathes a world in energy and dictates the very chemistry of its atmosphere, is the star, Our sun is dying. Not today, not tomorrow, not for another 5 billion years. But it's dying nonetheless. Every second, it converts millions of tons of hydrogen into helium, burning through its fuel in a controlled explosion that's been raging for 4.5 billion years. And when the fuel runs low, when the hydrogen in its core is exhausted, our star will swell into a red giant and consume the inner planets, Earth included. 5 billion years sounds like forever. It's longer than life has existed on this planet, longer than the continents have held their current shapes, longer than almost anything we can meaningfully comprehend. But in cosmic terms, it's a blink. The universe is 13.8 billion years old. Our sun will die when the universe is less than 20 billion years old. Just getting started, really. Still in its youth. And when our sun goes dark, there will be stars still shining. Trillions of them. Stars that were born billions of years before ours. Stars that are burning now. Stars that will continue burning long after every sun-like star in the galaxy has exhausted itself and gone cold. We call them M-dwarfs. Red dwarfs, the small ones, the weak ones. The stars nobody paid much attention to for most of human history. Could these smallest stars make the greatest homes? Let's talk about time, deep time. The kind that makes geological epochs look like heartbeats. An M-dwarf star, depending on its mass, can burn for 100 billion to 150 billion years. Some estimates push even higher. These aren't approximations with a margin of error. These are minimum lifespans based on fundamental physics, on how slowly these tiny stars consume their fuel. 100 billion years. The universe hasn't existed that long yet. It's not even close. Every M-dwarf star that's ever been born is still on the main sequence, still burning hydrogen, still in the prime of its life. Not one has aged into old age. Not one has died. They are, all of them, immortal by any standard we can relate to. And they're everywhere. M-dwarfs make up roughly 75% of all stars in the Milky Way. They outnumber sun-like stars 10 to 1. Most of them are invisible to the naked eye because they're so dim, but they're there, a hidden majority, a crimson ocean of patient, enduring light. What does this mean for planets? What does it mean for life? It means time, unimaginable stretches of it. Time for chemistry to explore every possibility. Time for evolution to stumble through dead ends and discover solutions. Time for ecosystems to collapse and rebuild and collapse again, and find new equilibria. Life on Earth has had roughly 4 billion years to evolve from simple chemicals and tidal pools to consciousness pondering its own origins. 4 billion years of mutation and selection, of extinction and radiation, of incremental change accumulating into transformative leaps. Now, imagine 20 billion years, 50 billion, 100 billion. What could life become with that much runway? We can't know. We lack the imagination. Evolution doesn't move in straight lines toward predetermined goals. It meanders. It experiments. It takes advantage of whatever opportunities the environment presents. Given enough time, given stable conditions, it creates things that seem impossible until they exist. And M-dwarfs offer something else beyond mere longevity. They offer stability. Our sun is a restless star. Its luminosity has increased by roughly 30% since it first ignited. That might not sound like much, but it's enough to doom a planet. If Earth had started its life with the atmosphere it has now, the extrasolar radiation would have triggered a runaway greenhouse effect billions of years ago. Our oceans would have boiled away. We'd look like Venus. We avoided that fate only because early Earth had a thicker atmosphere, more greenhouse gases to trap heat when the sun was cooler. As the sun brightened, geological processes removed carbon dioxide from the air, keeping temperatures in balance. It was a narrow path, a tightrope walk across billions of years. M dwarfs don't put their planets through that ordeal. Their luminosity changes, but glacially, imperceptibly. Over their 100 billion year lifespans, they brighten by perhaps 10 or 20%. That's it. A planet in the habitable zone of an M dwarf can maintain stable surface temperatures for unthinkable stretches of time. The rules don't keep changing. The goalposts don't move. Life doesn't have to constantly adapt to a shifting energy budget from its star. This is stability across epochs, consistency on a scale that makes Earth's climate look manic by comparison. If superhabitability is about giving life the best possible conditions, this might be the most important factor of all. Not warmth or wetness or the size of the planet, time and steadiness. The luxury of knowing that tomorrow will be like today, that 1,000,000 years from now will be like 1,000,000 years ago. That evolution can optimize for an environment that isn't perpetually in flux. It's tempting to imagine these worlds as paradises, as gardens locked in eternal spring, bathed in soft red light, their ecosystems humming along in perfect equilibrium for geological eras that dwarf anything Earth has known. But there's a catch. There's always a catch. Red light. M dwarfs are cool stars. Their surface temperatures range from about 2,000 to 4,000 Kelvin compared to our sun's 5,700 Kelvin. That difference in temperature shifts their spectrum. They emit most of their energy not in the visible wavelengths our eyes evolved to perceive, but in the infrared. Stand on a planet orbiting an M dwarf and the sun wouldn't look yellow or white. It would glow a deep, dull red, like an ember, like a coal that's still hot but no longer flaming. And the light reaching the surface wouldn't feel like sunlight. Not to us. It would be dimmer, redder, alien. Does that matter for life? Can photosynthesis work under red light? The answer is yes, but differently. Photosynthesis on Earth has optimized itself for the sun's spectrum. Plants absorb blue and red light and reflect green, which is why forests look the color they do. But that's not the only way to harvest light. It's just the way that worked here. On an M dwarf world, evolution would find different solutions. Plants, if that's even the right word for them, might be black to absorb every available photon, or deep purple, or iridescent, shimmering with pigments designed to capture the narrow wavelengths a red star provides. Life wouldn't look like Earth life. It couldn't. The energy available is different, less abundant per square meter. The photosynthetic chemistry would have to be more efficient, more desperate, squeezing every last bit of usable work from each photon that makes it through the atmosphere. And there's another problem. Infrared radiation penetrates water differently than visible light. On Earth, photosynthesis happens in the ocean's sunlit surface layers, the top 100 meters where light can reach. Below that is the aphotic zone, the darkness, the realm of creatures that live off falling detritus or geothermal energy from volcanic vents. On an M dwarf world, the boundary between light and dark might be shallower, much shallower. The ocean could be darker, colder, less friendly to the kind of prolific photosynthetic blooms that oxygenated Earth's atmosphere and built the base of our food chain. Or maybe not. Maybe life finds a way. Maybe the stability of these stars, the sheer duration they provide, gives evolution enough time to solve problems we think are insurmountable. Maybe after 10 billion years under red light, oceans teem with organisms we can't begin to picture, metabolisms we'd classify as impossible if we saw them in a lab. But we can't assume. We can't let hope override physics. The truth is, we don't know yet what red light does to the prospects for complex life. We have theories, models, educated guesses based on biochemistry and evolutionary principles, but no data, no examples, no catalog of exoplanet ecosystems we can study and compare. We're still searching, still learning, still trying to understand what makes a world not just habitable, but vibrantly, undeniably alive. And there's something poetic about that, isn't it? the smallest stars, the ones we overlooked for so long, might turn out to be the best hosts, the most patient gardeners, the ones that give life the ultimate gift, time enough for anything to happen. They'll be here long after stars like our sun have burned out, long after the universe has expanded and cooled, after galaxies have collided and merged, after star formation has slowed to a trickle, and the cosmos enters its long, quiet autumn. M dwarfs will still be shining, red and steady and tireless, keeping vigil over worlds that might, just might, have used all that time to become something extraordinary. But the gift of time comes with a price. To live near a long-lived red sun, a world must risk something Earth has never known. Imagine a world where the sun never moves, not across the sky, not at all. It hangs there, fixed in place, a red ember burning at the same spot on the horizon forever. No sunrise, no sunset, no passage of day into day again. On one half of the planet, eternal day, baking heat, a glaring red sun that never sleeps, never sets, never grants relief. On the other half, eternal night, perpetual darkness, cold that seeps into the rocks themselves, freezing whatever. Moisture exists into solid ice that will never melt. This is tidal locking. This is what happens when a planet orbits close to its star, when the same gravitational forces that raise tides in Earth's oceans grab hold of an entire world and slow its rotation until one face always looks toward the star and the other always looks away. Earth's moon is tidally locked to us. We always see the same lunar face. The far side remains hidden, turned eternally toward the cosmos. And for planets orbiting M dwarfs, tidal locking isn't rare, it's inevitable. Because M dwarfs are dim, their habitable zones are close, Mercury close. Closer, sometimes. A planet needs to orbit just a few million kilometers from its star to receive enough warmth for liquid water. At that distance, tidal forces are intense. Within a few 100 million years, perhaps less, the planet's rotation locks. One hemisphere becomes the day side, the other becomes the night side. The boundary between them, the narrow ring where the sun sits forever on the horizon, has a name: the Terminator. A world frozen and scorched, yet possibly alive. Let's talk about the Terminator first, this twilight zone. This ribbon of eternal dusk that encircles the planet like a belt. Here, the sun doesn't glare overhead. It hovers just above the horizon, casting long shadows that never shorten, painting the landscape in perpetual reds and oranges and deep crimsons. The light comes in at a low angle, diffused, gentler than the direct radiation hammering the subsolar point at the center of the day side. Temperatures here might be mild, stable. Not the searing heat of the day side, not the frozen desolation of the night. Somewhere in between. Goldilocks conditions, ironically, on a world that seems to defy everything we think of as habitable. If liquid water exists anywhere on a tidally locked planet, it might pool here. Rivers fed by melting ice from the night side might flow through this band before evaporating on their way toward the day. Lakes could form in crater basins, perhaps even oceans, wrapped around the planet like a ring hugging the Terminator. And if water exists, life could exist. Not everywhere. Not thriving across continents and oceans like on Earth. But here, in this narrow habitable zone, in this sliver of eternally mild twilight, evolution might find a foothold. It's a strange picture, a ribbon world, a place where every location has one permanent environment, unchanging across billions of years. No seasons, no day-night cycles, just endless consistency. A tree rooted in the Terminator would experience the same light, the same temperature, the same conditions for its entire lifespan. For organisms adapted to such an environment, it might be paradise. Stability taken to its logical extreme. No need to prepare for winter, to store energy for the night, to endure cycles of feast and famine as the planet turns. just one long, uninterrupted existence in the only climate that matters. But how wide? Is the Terminator? How much space does life have to work with? That depends on the atmosphere, on whether air can move heat around the planet efficiently enough to broaden the habitable zone. We'll come back to that, because the atmosphere is everything on a tidally locked world. But first, there's something else happening, something hidden beneath the surface, a source of heat that has nothing to do with the star: tidal heating. Remember, these planets orbit close. The gravitational pull from their star is immense. But gravity doesn't just lock rotation. It stretches, it squeezes, it kneads the planet like dough, raising tides in solid rock, flexing the interior, generating friction. On Earth, tidal heating is modest. The moon raises tides in our oceans, creates a tiny bit of friction in our crust, but it's negligible compared to the heat left over from the planet's formation and the heat generated by radioactive decay. But on a tidally locked world orbiting an M-dwarf, especially one with even slight orbital eccentricity, the tidal forces can be staggering. If a planet's orbit isn't perfectly circular, if it's even a little bit elliptical, the distance to the star changes throughout each orbit, closer, then farther, then closer again. The gravitational force varies, the tidal bulge shifts, the planet's interior flexes repeatedly, and all that mechanical work converts into heat. How much heat? Calculations suggest some tidally locked planets could experience tidal heating 100, 200, even 300 times greater than Earth's entire internal heat budget. That's not a typo. 300 times. That kind of energy doesn't just warm the interior, it melts it, drives volcanic activity on a scale we've never witnessed, creates a furnace within. Jupiter's moon, Io, is tidally heated. It's the most volcanically active body in the solar system, its surface constantly resurfacing with fresh lava, its atmosphere fed by volcanic plumes. And Io is a moon. Imagine that process scaled up to a planet 4 times the mass of Earth. On the right world, tidal heating could be a gift. It could warm the night side from below, preventing the atmosphere from freezing out and collapsing into frost on the dark hemisphere. It could drive plate tectonics even more vigorously than on Earth, recycling volatiles, regulating climate, keeping the planetary thermostat running smoothly. But too much tidal heating? That becomes catastrophic. Volcanoes everywhere, constant eruptions flooding the surface with lava, choking the atmosphere with sulfur dioxide and ash. A runaway greenhouse effect triggered by outgassing. Surface temperatures climbing until oceans boil, until rock begins to glow, until the planet becomes a hell world wrapped in thick clouds of superheated steam. It's a razor's edge. The right amount of tidal heating stabilizes and enriches. Too much destroys everything, and we can't know, from 22 light years away, which side of that edge Gliese 667 cc falls on. We know its mass, we know its orbit has some eccentricity. We can calculate that tidal forces are present, but whether they're nurturing or annihilating, that requires closer observation. Data we don't have yet. The planet remains a paradox, promising and perilous in equal measure. But let's assume the best case. Let's imagine a world where tidal heating is strong but not overwhelming, where volcanoes enrich the atmosphere with gases, where the night side stays warm enough to prevent atmospheric collapse, where the day side doesn't cook. Even then, the question remains, can this world actually sustain a habitable climate? The answer depends almost entirely on the atmosphere. Air moves, it's not static. Heat one part of a gas, and it rises, flows, carries energy with it. On Earth, atmospheric circulation distributes solar heat from the equator toward the poles. It moderates temperature extremes. It's why the tropics aren't as hot as they could be, and why the Arctic isn't as cold. On a tidally locked planet, the atmosphere has an even more critical job. It needs to move heat from the scorching day side to the frozen night side. It needs to prevent all the air itself from condensing as ice on the night side, leaving the day side an airless vacuum. Can it do that? Climate models suggest yes, if the atmosphere is thick enough. If there's sufficient pressure, sufficient mass of air to absorb and transport heat. Winds would be ferocious, super-rotating perhaps, rushing from the subsolar point outward in all directions, flowing around to the night side, warming it, then returning. The terminator would be a region of permanent storms, boundaries where hot air from the day side collides with cold air from the night. Cyclones that last for geological ages, rooted in place, fed by the eternal temperature gradient, but stable, predictable, knowable, not chaotic weather, but a fixed pattern. A planetary climate locked into one eternal configuration. If such an atmosphere exists, the habitable zone broadens. It's not just the narrow terminator anymore. Parts of the day side might be tolerable, cooled by winds and clouds. Parts of the night side might stay above freezing, warmed by atmospheric circulation and tidal heating from below. Life could spread, adapt to different bands of temperature and light. Ecosystems might stratify by latitude, by distance from the subsolar point, each region hosting organisms specialized for its particular eternal conditions. But without a thick atmosphere, without efficient heat transport, the night side freezes. Water vapor, carbon dioxide, nitrogen, everything condenses and falls as snow that never melts. The atmosphere itself migrates to the night side and locks up as frost. Pressure drops on the day side. What's left can't hold heat or moderate temperature. The day side becomes an airless desert, bombarded by radiation, baking under the relentless red sun. The planet becomes uninhabitable, not gradually, not over time, almost immediately on geological timescales. A rapid collapse into two dead hemispheres separated by a thin, transient zone of barely survivable conditions. This is the tidal-locked paradox. These worlds could be havens for life, stable and warm and rich with time. Or they could be split nightmares, frozen and scorched, hostile to anything resembling the biochemistry we understand. And we can't tell which they are until we look closely, until we study their atmospheres, map their temperatures, watch how their climates behave. Gliese 667 CC remains an enigma, a question mark in the galactic catalog. It has the mass to hold a thick atmosphere. It orbits in the habitable zone. Tidal heating could stabilize its climate or destroy it. We simply don't know. But if it survives its own contradictions, if it threads the needle between fire and frost, it may offer something Earth doesn't have, something super habitable in its own strange way. Oceans, not familiar oceans, not the blue waters of Earth, rolling with waves under a yellow sun, something else, something shaped by eternal twilight and ancient currents and the peculiar chemistry of a world that never turns. If a world can balance fire and frost, it may offer oceans. But oceans are not always kind. Water is life. We say it so often it's become a cliche. But cliches exist because they carry truth. And this one runs deeper than most. Every living thing we have ever found needs water. Not as a luxury, not as one option among many, as a requirement, a fundamental necessity woven into the chemistry of existence itself. Water dissolves, it transports, it moderates temperature, it participates in reactions while remaining stable enough to stick around. It's the universal solvent, the medium in which the molecular dance of life unfolds. So, when we search for habitable worlds, we search for water, liquid water, oceans and seas and rivers where chemistry can happen, where molecules can meet and interact and build the complex structures that eventually become biology. More water should mean more life, right? More opportunity, more space for evolution to experiment, more habitable real estate where organisms can diversify and spread, But how much water is too much? On Earth, roughly 70% of the surface is ocean. The rest is land, continents, islands, shallow coastal shelves where sunlight reaches the seafloor and photosynthesis can thrive. Tide pools, estuaries, reefs. The boundary zones where water meets rock, where nutrients flow, where ecosystems flourish in spectacular abundance. These boundaries matter. They matter enormously. Life began in the ocean, yes. But life exploded in diversity when it found the edges. When it colonized the coasts, adapted to the intertidal zones, eventually crawled onto land itself. The variety of environments near shorelines, the mixing of marine and terrestrial nutrients, the rhythmic changes of tides, all of it drove evolutionary innovation. Take away the continents and you lose those hot spots. You lose the shallow seas. You lose the fracture zones where tectonic plates pull apart and create new seafloor, where volcanic activity enriches the water with minerals, where hydrothermal vents spew chemicals that fuel entire ecosystems independent of sunlight. Replace Earth's geography with a single, planet-spanning ocean 10 kilometers deep. And what do you get? Probably a lot less life, certainly a lot less diversity. Deep oceans are biological deserts, not lifeless, but sparse. In the open ocean, far from coasts and far from the seafloor, there's not much to work with. Nutrients are scarce. They fall as marine snow, drifting down from the sunlit surface layers where photosynthesis happens. Most life clusters near the top, where light penetrates, or near the bottom, where organic matter accumulates. The vast middle is mostly empty, dark and cold and quiet. A world entirely covered in deep ocean might have life, but it would be concentrated in thin films, a photosynthetic layer near the surface, a scavenging layer near the seafloor, perhaps some free-floating organisms in between, but nothing like the explosive diversity of Earth's continental shelves and coral reefs and tide pools. So, more water isn't automatically better. At some point, too much water becomes a limitation. But what about the opposite scenario? Not too much water, but just enough, distributed in a way that maximizes habitability. For a superhabitable world, you'd want oceans covering perhaps 60 to 80% of the surface, enough water to moderate climate, to create humidity, to drive weather systems and ocean currents, but also land, archipelagos, shallow seas, continental shelves that stretch for thousands of kilometers, coastlines that provide endless ecological niches. The question is, what does Gliese 667c have? We don't know. We can't see its surface, can't map its oceans or continents, can't measure how much of it is water and how much is rock. But we can make educated guesses based on how planets form, based on where it orbits, based on the energy it receives from its star. And those guesses lead us to a problem. Gliese 667 CC sits close to its star, close enough to be tidally locked, close enough to receive roughly 90% of the sunlight Earth gets. Even though its star is much dimmer than ours, 90% sounds safe, sounds comfortable. Just a little less than Earth, which means slightly cooler temperatures, right? Not necessarily. Because Gliese 667c, C orbits an M-dwarf, and M-dwarfs emit most of their energy in the infrared. Infrared radiation behaves differently than visible light. It's absorbed more efficiently by water vapor, by carbon dioxide, by greenhouse gases. A planet receiving 90% of Earth's total solar energy, but with most of that energy in the infrared, could actually be warmer than Earth, much warmer. If it has a thick atmosphere with even modest amounts of water, vapor or CO2, the greenhouse effect intensifies, temperatures rise, and there's a threshold, a point of no return, where heat becomes self-reinforcing. We call it the runaway greenhouse effect. It's what happened to Venus. Venus receives about twice as much solar energy as Earth. Early in its history, it may have had oceans. but the extra heat evaporated water faster than geological processes could remove it from the atmosphere. Water vapor is a powerful greenhouse gas. More evaporation meant more warming, which meant more evaporation, which meant more warming, in a feedback loop that didn't stop until the oceans boiled away entirely and surface temperatures climbed above 400 degrees Celsius. Venus is a cautionary tale, a reminder that habitable zones have boundaries, and the inner edge, the boundary closest to the star, is sharp and unforgiving. Gliese 667 c sits near that edge, not necessarily past it, but uncomfortably close. If it has too much water vapor in its atmosphere, if the greenhouse effect tips just slightly too strong, it could spiral into uninhabitability despite being in the so-called habitable zone. This is where the ocean world dilemma becomes acute. Water is essential, but water vapor is dangerous. Oceans moderate climate, but too much ocean surface area means too much evaporation. It's a balance, a narrow path between too dry and too wet, between ice world and steam world. If Gliese 667 cc has survived this long without crossing into a runaway greenhouse, it suggests careful balance. Perhaps its atmosphere is thin enough to prevent too much heat retention. Perhaps clouds reflect enough sunlight back into space to compensate. Perhaps the tidal locking helps, creating a permanent cold trap on the night side, where water vapor condenses and locks away, preventing it from building up on the day side. That last possibility is particularly interesting. It leads to a scenario planetary scientists call the eyeball world. Picture this: a tidally locked planet with a single ocean on the day side, directly facing the star. Liquid water in the warmest zone, surrounded by land, bordered by ice as you move toward the terminator and beyond into the night side. From space, it would look like an eye, a blue pupil of ocean staring eternally at the red sun, ringed by brown or green land, fading into white ice. The night side would be frozen solid, a shell of ice kilometers thick, covering frozen ground, no liquid water. Maybe a subsurface ocean, kept liquid by tidal heating from below, trapped beneath the ice and inaccessible to the surface. All the action, all the life, would happen on the day side, in that single ocean, in the land surrounding it, in the twilight regions where ice begins to melt and streams flow toward the central sea. It's a bizarre geometry, nothing like Earth, but it could be stable. The ice on the night side acts as a reservoir, a long-term storage for water that doesn't contribute to atmospheric greenhouse effects. The dayside ocean is limited in size, which limits evaporation. The planet maintains a balance that allows it to stay in the habitable zone without tipping into a runaway. Life on an eyeball world would be concentrated, crowded into one hemisphere. Species would never experience true night, never see stars hidden behind eternal daylight or blocked by the planet itself on the night side. But they would have an ocean, a single stable body of water bathed in red light. Currents driven by temperature differences, by the rotation of winds around the subsolar point. Coastlines that never change. Tide pools without tides because the star never moves. Evolution would find a way. It always does. Given enough time, given stable conditions, life would fill every niche that ocean and its shores could provide. But would it be diverse? Would it be rich? That depends on the details, on how large the ocean is, on whether there are islands, shallow regions, variations in depth and temperature, and nutrient availability, on whether the chemistry supports complex food webs or just simple microbial mats. An eyeball world could be a paradise, or it could be a monotonous expanse of sameness, lacking the geographical diversity that drives speciation. We can't know, not yet. Not without going there, or at least getting close enough to observe with instruments sensitive enough to map surfaces and measure atmospheric composition, and detect signs of geological activity. But here's what we can say. If Gliese 1667 CC has oceans, it has avoided the runaway greenhouse. It has threaded the needle. It sits in a precarious position, warmed by a dim star, possibly heated from within by tidal forces, holding on to an atmosphere thick enough to circulate heat, but not so thick it traps itself in a death spiral. That's not nothing. That's remarkable, actually. That's a world that solved problems Earth never had to face. And if it has solved those problems, if it has stabilized its climate against odds that would doom most planets, then perhaps it has something else. Something we've been searching for since we first pointed telescopes at the stars. Perhaps it has life. Not Earth life, not forests and whales and birds, but something. Chemistry that's crossed the threshold into biology. Patterns that replicate, evolve, persist. Life that's adapted to red light and eternal day. Life that's never known seasons or night. Life that exists in an ocean geometry we'd find alien and unsettling, but life nonetheless. The question is, how would we know? We can't see organisms from 22 light years away. Can't watch them swim or photosynthesize or reproduce. Can't land a rover and scoop up samples. All we can do is look at the planet as a whole, at its atmosphere, at the light reflected from its surface and filtered through its air, and search for fingerprints, chemical signatures, the unmistakable markers that something down there is alive and altering its world. But even if oceans form and climates stabilize, how would we know? What fingerprints would alien life leave behind? There's oxygen in Earth's atmosphere. 21% of the air you're breathing right now is O2, oxygen molecules. Two atoms bonded together, eager to react with almost anything they touch. It's corrosive stuff, really. Rust is just iron meeting oxygen. Fire is rapid oxidation. Left to itself, oxygen would bind to rocks, to metals, to organic molecules, and disappear from the air within a few million years. But it doesn't disappear. It stays. It replenishes itself faster than chemistry can consume it, because life makes it. Photosynthesis, the process that turns sunlight and carbon dioxide and water into sugar and oxygen. Plants do it, algae do it, cyanobacteria have been doing it for over 2 billion years, pumping oxygen into the atmosphere, transforming Earth from a reducing world to an oxidizing one, creating the air that animals like us need to exist. Oxygen is a biosignature, a fingerprint of life, a molecule so unstable, so reactive, that its persistent presence in an atmosphere screams that something down there is actively producing it. If we point our telescopes at an exoplanet and detect oxygen in its spectrum, we know something remarkable is happening on that world. But how would a superhabitable world announce itself? What would its biosignatures look like? If the theory is right, if superhabitable planets provide more stable climates, more time for evolution, better conditions for life to flourish, then perhaps their biosignatures would be stronger, louder, more obvious than Earth's. Imagine an ocean world with shallow seas covering 70% of its surface, continents fractured into archipelagos, creating endless coastlines, a star that shines steadily for 100 billion years, giving evolution unimaginable time to optimize photosynthesis, to fill every niche, to build ecosystems of staggering productivity. On Earth, photosynthetic organisms produce roughly 100 billion tons of oxygen per year. It's enough to maintain atmospheric concentrations around 21%, despite constant consumption by respiration, decay, and geological processes. But Earth's photosynthesis is limited by nutrient availability, by seasonal changes, by the fact that large portions of the planet are too cold, too dry, or too dark for robust growth. A superhabitable world might not have those limitations. Its climate might be warmer on average, more humid, more stable. Its shallow seas might be richer in nutrients, constantly replenished by volcanic activity, and efficient recycling through plate tectonics. Its red dwarf star might shine steadily for tens of billions of years, never brightening enough to force evolutionary adaptation, just providing constant, reliable energy. Life on such a world could become astonishingly productive. Photosynthetic organisms covering vast portions of the ocean's surface, dense forests, or their alien equivalents on land. Ecosystems so rich, so efficient at capturing energy and cycling nutrients that oxygen production exceeds anything Earth has achieved. Atmospheric oxygen could climb to 25%, 30%, perhaps higher. More than Earth has ever sustained, even during the most productive periods of our geological history. That would be a beacon, a signal visible across light years. Spectroscopic analysis would show oxygen absorption lines far stronger than ours, unambiguous evidence that something down there is alive and thriving. But oxygen isn't the only biosignature we should look for. It's just the one we know best because it's the one Earth produces. Life is chemistry, and chemistry offers many pathways, many metabolisms, many ways to harvest energy and build structures and leave traces in the atmosphere. Consider dimethyl sulfide, DMS, a molecule with 2 carbon atoms, 6 hydrogens, and 1 sulfur, arranged in a simple structure that smells faintly of cabbage or sea spray. On Earth, marine algae produce DMS as a byproduct of their metabolism. It escapes into the atmosphere, where it plays a role in cloud formation and climate regulation. It's present in tiny amounts, parts per trillion, easy to overlook, but it's there, and it's biological. No known geological process produces DMS in significant quantities. Its presence in an atmosphere is a potential biosignature, a chemical calling card of life. On a superhabitable ocean world, DMS production could be vastly more significant. If life is optimized for different metabolic pathways under red light, if sulfur plays a more prominent role in the biochemistry than it does on Earth, atmospheric DMS levels could be detectable from interstellar distances. Sulfur itself is interesting. It's abundant in the universe. It participates in energy-yielding reactions. On Earth, some bacteria use sulfur compounds instead of oxygen for respiration. They thrive around hydrothermal vents, in deep ocean sediments, in environments that existed long before oxygen filled the air. On a world orbiting an M-dwarf, where infrared radiation dominates and photosynthesis might work differently, sulfur-based metabolisms could be more common, perhaps even dominant. Life could evolve to use sulfur cycles the way Earth life uses oxygen and carbon, creating atmospheric signatures we'd find strange and unexpected. Dimethyl sulfide might not be alone. There could be other sulfur-bearing molecules: hydrogen sulfide, carbonyl sulfide, sulfur dioxide produced biologically rather than volcanically in ratios that defy geological explanation. These would be exotic biosignatures. Signatures of life? Yes, but not life as we know it. Not Earth life translated to another world. Something adapted to different conditions, different energy sources, different constraints. And then here's where the search becomes challenging. Because we're looking for patterns we recognize, chemical combinations that make sense to us based on our understanding of terrestrial biology. What if life on superhabitable worlds doesn't mimic Earth's chemistry at all? What if it uses molecules we haven't considered? Metabolic pathways our biochemistry textbooks don't describe? What if it leaves fingerprints in the atmosphere that look to us like nothing more than geological noise? This is the problem of anti-biosignatures, or perhaps more accurately, the problem of invisible biosignatures. Not anti in the sense of evidence against life, but invisible because we don't know how to read them. We assume oxygen is a strong biosignature because we can't imagine non-biological processes that would maintain it in an atmosphere long term. But that assumption rests on our knowledge of Earth chemistry. If we encountered a world with abundant atmospheric oxygen produced entirely by photochemistry, by some exotic geological process we haven't discovered yet, we'd be wrong. Similarly, the absence of oxygen doesn't mean the absence of life. Earth's atmosphere had no free oxygen for the first 2 billion years of life's existence. Microbial ecosystems thrived in oceans and sediments, cycling nutrients, evolving complexity, building the foundation for everything that came later. From space, during those eons, Earth would have looked lifeless. No obvious biosignatures, nothing to announce that the world below was teeming with biology. We could be making the same mistake with exoplanets, dismissing worlds that look chemically boring, atmospheres in equilibrium, no obvious signs of active biology, when in fact, those worlds are inhabited by organisms so different from Earth life that their chemical signatures don't register as anomalous to us. Life that breathes different gases, metabolizes different compounds, alters its environment in ways we haven't learned to recognize. This is why the search for biosignatures is as much about expanding our imagination as it is about building better telescopes. We need to think beyond Earth analogs, beyond oxygen and methane and the handful of molecules we confidently call biosignatures. We need to ask, what would chemistry look like if it were alive? What patterns, what disequilibria, what combinations of molecules would indicate biology rather than geology? And we need to be humble enough to admit we might miss it, that a superhabitable world could be staring us in the face, alive and thriving, and we wouldn't know because we're looking for the wrong signals. Gliese 667 cc could have an atmosphere rich in oxygen. It could reek of dimethyl sulfide and sulfur compounds. It could show spectral lines we've never seen before, molecules produced by metabolisms we haven't dreamed of. Or it could look quiet, inert, uninteresting, its biosignatures subtle, woven into the chemistry in ways we don't yet understand. The only way to know is to look, really look, not with a glance, not with a few hours of telescope time, but with sustained observation. Detailed spectroscopy, measurements taken across multiple wavelengths, multiple seasons if the planet has them, multiple years. We need to watch how the atmosphere changes, if it changes. Track variations that might indicate biological activity. Build models that can distinguish between living chemistry and dead chemistry, between worlds that are merely habitable and worlds that are inhabited. But there's a problem, a rather significant one we haven't mentioned yet but can't ignore any longer. For all our speculation about Gliese 667 cc, for all the calculations and models and theories about its mass and orbit and potential habitability, there's something we need to address, something fundamental. We're not entirely certain the planet exists. The data that announced its discovery, the radial velocity measurements that detected its gravitational tug on its star, have been questioned, reanalyzed, debated in scientific papers and conferences. Some researchers argue the signal is real. Others suggest it might be noise, an artifact of stellar activity, a pattern in the data that looks like a planet but isn't. This is not uncommon in exoplanet science. Detection methods are indirect. We don't see the planets themselves, not usually. We infer their existence from tiny wobbles in starlight, from brief dimming as they pass in front of their stars, from gravitational effects measured in meters per second. It's detective work, and sometimes the clues are ambiguous. Gliese 667 cc remains in that ambiguous space. Probably real, possibly real, but not confirmed with the certainty we'd like. And that raises an uncomfortable question. Before we can analyze its atmosphere for biosignatures, before we can determine if it's an ocean world or an eyeball world or a drowned mini Neptune, we need to be sure it's actually there. We need to see it, not infer it, see it. But before we can search deeply, we must be sure the world is even there, and that is not always certain. When stars pretend to have worlds. In 2013, astronomers made an announcement that sent ripples through the scientific community and captured headlines around the world. The Gliese 667 system, a triple star configuration just 22 light-years from Earth, appeared to host something extraordinary. Not one potentially habitable planet, not two, but three. Three super-Earths orbiting in the habitable zone of Gliese 667c, the smallest star in the system. Three worlds where liquid water could theoretically exist. Three chances for life to emerge, evolve, flourish. It was a revelation, a system packed with possibility. The kind of discovery that makes you reconsider everything you thought you knew about planetary formation, about how common habitable worlds might be, about our place in a universe suddenly teeming with potential homes for life. The findings came from radial velocity measurements, the technique that watches a star for the tiny wobbles caused by orbiting planets. As a planet circles its star, its gravity tugs the star back and forth. The star moves toward us, then away, then toward us again. That motion shifts the wavelength of its light through the Doppler effect. Blue shifted when approaching, red shifted when receding. By measuring these shifts with exquisite precision, down to meters per second, astronomers can infer the presence of planets, calculate their masses, determine their orbital periods. It's an elegant method, proven, responsible for discovering hundreds of exoplanets. But it's not infallible. The 2013 announcement described a packed habitable zone, planets labeled B, C, E, F, and G, some in the zone, some near it. The research painted a picture of a system where real estate for life was abundant, where worlds crowded together in the narrow band of orbital distances that would allow liquid water. It looked too good to be true, and as it turned out, parts of it were. Science is self-correcting. It has to be. Initial discoveries get scrutinized, reanalyzed, challenged. Other teams examine the same data. New observations are made. Models are refined. Errors, if they exist, come to light. And that's what happened with Gliese 667c. Later studies, using additional data and more sophisticated analysis techniques, began to raise questions. The signals for some of those planets, particularly E, F, and G, started looking suspicious. Less like the clean periodic signatures you'd expect from orbiting worlds. More like noise. More like something else mimicking planetary signals. Something coming from the star itself. Stars are not static. They're not smooth, uniform spheres of light. They're roiling dynamos of plasma, shot through with magnetic fields, covered in features that appear and disappear and evolve over time. Star spots, dark patches on the stellar surface, cooler than their surroundings, caused by intense magnetic activity. They're like sunspots on our own sun, but on M dwarfs they can be larger, more numerous, more persistent, and they cause problems. When a star spot rotates across the face of a star, it changes the star's spectrum. The spot is cooler, so it emits less light in certain wavelengths. That alters the overall color balance of the starlight reaching us. And because different wavelengths shift differently in the Doppler effect, it can create the illusion of radial velocity variation. It looks like the star is moving toward us and away from us. It looks like there's a planet tugging on it, but there's no planet, just a dark spot rotating with the star's surface, creating a false signal that repeats with the stellar rotation period. This is stellar activity noise, and it's insidious, because it mimics exactly what we're looking for. Periodic variations, repeated patterns, all the hallmarks of an orbiting planet. Distinguishing real planets from stellar imposters requires careful work. You need to correlate radial velocity data with other measurements, activity indicators, spectral line, shapes, photometric monitoring to track brightness changes caused by star spots. When researchers did this for Gliese 667c, the picture changed. The signals for planets E, F, and G grew weaker, less convincing. The patterns appeared more consistent with stellar rotation and magnetic cycles than with gravitational tugs from actual worlds. The packed habitable zone began to empty. Current consensus suggests that only 2 planets are confidently confirmed: Gliese 667cb and Gliese 667cc. The others? Questionable, possibly artifacts, ghosts in the data created by a star's own restless surface. And even Planet C, the one we've been discussing, the super-Earth in the habitable zone, the world that might be ocean-covered or tidal-locked or rich with exotic biosignatures, even it remains somewhat uncertain. Real, probably, but not beyond all doubt. This is humbling, frustrating even. Here's a star system close enough that we can study it in detail, bright enough that we can gather good data, interesting enough to justify decades of observation. And we still can't say with complete certainty what planets orbit there. The universe is not making this easy for us, and M-dwarfs, as much as we love them for their longevity and abundance, are particularly difficult hosts to study. Part of the problem is what astronomers call red noise. Not noise in the colloquial sense of random static, but noise with structure. Variations that happen on long time scales, that evolve slowly, that can masquerade as planetary signals because they have periodicities similar to what orbiting worlds would produce. M-dwarfs are magnetically active, their surfaces churn, their spots come and go. Their rotation periods can be anywhere from days to months, and those rotation cycles create signals in the radial velocity data that repeat, that look orderly, that seem like they could be planets. Add to that the fact that M-dwarfs are dim. To maintain a given signal-to-noise ratio in measurements, you need longer exposure times, more photons, more observation nights. The data takes longer to accumulate, and during that time, the star itself is changing, evolving, complicating the picture. Finding real Earths around quiet red suns becomes an exercise in patience and precision. You need years of data, multiple independent detection methods, transit observations if you're lucky enough to have the planet pass in front of its star from our perspective, direct imaging if the technology advances far enough. But even then, uncertainty lingers. Because stars are counterfeiters, they produce false signals, they wear masks. This doesn't mean exoplanets around M-dwarfs don't exist. They clearly do. We've confirmed hundreds of them, some through radial velocity, some through transits, some through multiple methods that cross-verify each other and eliminate doubt. But it does mean the early catalogs, the initial announcements, the exciting claims of multiple habitable worlds in a single system, those need to be taken with caution, treated as provisional until confirmed, understood as snapshots of our knowledge at a particular moment, subject to revision as we learn more. The 2013 claim of a packed habitable zone around Gliese 667c was not fraud. It was not incompetence. It was scientists working with the best data and methods available at the time, making inferences that seemed justified, announcing results that seemed robust. But science advances, techniques improve. Longer baselines of observation reveal patterns that shorter data sets miss. And sometimes, what looked like a breakthrough discovery becomes a cautionary tale about the complexity of distinguishing signal from noise. Does this mean we should abandon the search, dismiss M-dwarfs as too problematic, too noisy, too difficult to study? No. Exactly the opposite. It means we need to be smarter, more careful, more sophisticated in our methods. It means we need to invest in better instruments, longer observing campaigns, more advanced algorithms for disentangling stellar activity from planetary signals. Because the potential is still there. M dwarfs still outnumber sun-like stars. They still offer stability and longevity. Their habitable zones are still within reach of our current technology. The promise of superhabitable worlds around red suns hasn't vanished. It's just become more elusive. And perhaps that's fitting. Perhaps the universe should be difficult to read. Perhaps the answers we seek should require effort, ingenuity, persistence. Easy discoveries, obvious patterns, those don't teach us much. They don't push the boundaries of what we can measure and understand. They don't force us to develop new techniques, new ways of seeing. The hard problems, the ambiguous signals, the stars that fool us with their spot patterns and magnetic cycles, those are the ones that drive progress. That make us better observers, better scientists. Gliese 667c, for all its uncertainties, has taught us lessons about stellar activity, about the limitations of radial velocity methods, about the need for multi-method confirmation, about humility in the face of data that whispers rather than shouts. And even if Planet C turns out to be a phantom, even if further analysis downgrades it from probable to possible to unlikely, the search continues. The question remains, are there superhabitable worlds orbiting M dwarfs, planets larger than Earth, warmer, wetter, more stable, worlds where life has had tens of billions of years to flourish under a patient red sun? The answer is almost certainly yes. The galaxy is vast. M dwarfs are numerous. The laws of planetary formation don't forbid such worlds. They might even favor them under the right conditions. We just haven't confirmed one yet. Haven't found that perfect example, that unambiguous detection, that world we can point to and say with confidence, there, that's it. That's a super habitable planet. But we're looking, and we're getting better at it. And every false positive, every mistaken detection, every star that counterfeited a planet and got caught teaches us something valuable. It teaches us to look closer, to ask harder questions, to demand better evidence. And, in a strange way, the difficulty makes the search more meaningful, because when we finally do confirm a super-habitable world, when we detect its atmosphere and measure its biosignatures and prove beyond doubt that it's real and alive and thriving, we'll know we earned that knowledge. We'll know it's not a mistake, not stellar noise, not wishful thinking projected onto ambiguous data. It will be real, a genuine other world. A place where life might exist in forms and abundances we can barely imagine. Yet the doubt only deepens the mystery. If even nearby stars can fool us, what else lies hidden across the galaxy? If superhabitable worlds are common, where is everyone? It's a question that echoes across decades of astronomical discovery. A question that becomes more pressing with every exoplanet we find, every potentially habitable world we catalog, every star system that might host the conditions for life. We call it the Fermi paradox, after the physicist Enrico Fermi, who supposedly asked it over lunch one day in 1950. If intelligent life is common in the universe, if technological civilizations arise on a meaningful fraction of habitable worlds, then where are they? Where are the radio signals, the megastructures, the evidence of intelligence reshaping matter and energy on cosmic scales? The galaxy is old, 13 billion years in the making. Stars like our sun have existed for 10 billion years. Planets have been forming almost since the beginning. If life is easy, if intelligence is inevitable given enough time, then someone should have arisen long before us. Someone should have spread across the galaxy, colonized other star systems, left traces we couldn't miss. The silence is deafening. And if superhabitable worlds exist, if there are planets out there offering better conditions than Earth, more time for evolution, more stability for civilizations to develop, then the paradox deepens. Because those worlds should be the ones producing life. Abundant life, complex life, maybe even intelligent life. So, where is everyone? Let's start with a concept astronomers call the principle of mediocrity. It's the idea that there's nothing special about Earth, Nothing unique about our position in space, our place in time, our star, our planet. We're typical, average, mediocre in the most technical sense of the word. The principle has served us well. It guided Copernicus when he placed the sun at the center of the solar system rather than Earth. It informed our understanding that the Milky Way is one galaxy among billions, that our sun is one star among hundreds of billions, that planets are common rather than rare. Mediocrity as a philosophical stance teaches humility. It reminds us not to assume we're the center of anything, the template for anything, the measure of anything. But what if we've applied it incorrectly? What if Earth isn't mediocre? What if we're not typical at all? Not because we're superior, not because we're favored by cosmic design, but because we're merely adequate, barely sufficient, the minimum viable conditions for complex life rather than the optimal ones. Think about it. Earth orbits a yellow dwarf star that's already halfway through its main sequence lifetime. We have maybe another billion years of habitability before the sun's increasing luminosity triggers a runaway greenhouse effect. That's not much time, cosmically speaking, a blink compared to the 100 billion years an M-dwarf offers. Our planet has endured multiple mass extinctions, ice ages that nearly froze the entire surface, impact events that vaporize portions of the crust, volcanic episodes that choke the atmosphere with ash and sulfur. We've survived, but barely. Evolution has been repeatedly reset, forced to rebuild complexity from whatever organisms managed to cling on through catastrophic bottlenecks. And our climate is fragile. Small changes in atmospheric composition, in ocean currents, in ice sheet coverage, all of it cascades into dramatic shifts. We teeter on the edge of stability, always have. Now imagine a world that doesn't have these problems. A super Earth with more mass, stronger plate tectonics, better climate regulation, orbiting an M-dwarf that shines steadily for epochs Earth will never see. Fewer extinction events, more continuous development, time for evolution to explore possibilities we haven't glimpsed. If such worlds exist, and the physics suggests they should, then maybe life doesn't just survive there. Maybe it thrives. Maybe it reaches complexities we can't imagine, builds ecosystems of extraordinary richness, perhaps even develops intelligence and technology while Earth was still lifeless rock. The principle of mediocrity reversed. Earth is the outlier, the marginal case, the world that barely made it into the habitable category. Life might prefer quieter stars, slower climates, gentler eons where adaptation doesn't require constant response to catastrophe. So, again, where is everyone? One possibility is that we're early, that despite the galaxy's age, despite the eons available for life to emerge, the first intelligent civilizations are only just beginning to appear. We might be among the earliest technological species, and the others, if they exist, are too young or too far away to have made contact. It's a comforting thought, lonely but not depressing. We're pioneers, the first wave, the ones who will eventually meet others as they develop. But there's another possibility, a darker one, the Great Filter. The concept proposes that somewhere between lifeless chemistry and galaxy-spanning civilizations, there's a step that's extraordinarily difficult. So difficult that it filters out most attempts. A barrier that almost nothing gets through. The question is, where is the filter? If it's behind us, if the hard step is the emergence of life itself, or the development of complex cells, or the evolution of intelligence, then we've already passed it. We're through the bottleneck. The galaxy might be full of microbial life, but empty of minds. And we're one of the rare exceptions that made it to technology. But if the filter is ahead of us, if the hard step is something civilizations face after they become technological, then the silence makes sense in a more troubling way. Civilizations arise, develop, reach a certain point, and then something stops them. Nuclear war, environmental collapse, artificial intelligence gone wrong, resource depletion, something that's difficult to avoid, that catches nearly everyone. The silence isn't because intelligence is rare, it's because intelligence is unstable. And here's where superhabitable worlds complicate the picture. If such worlds are common, if they offer better conditions for life to emerge and evolve, then life should be common. The early filters, the hard steps of abiogenesis and complexity, should be easier to pass on worlds with more time and more stability. Yet, if the galaxy were full of living worlds, if superhabitable planets orbiting M-dwarfs were teeming with ecosystems, we'd expect to see something. Chemical signatures in exoplanet atmospheres, anomalous patterns that hint at widespread biology, evidence that life has taken hold across countless star systems. We're only beginning to look, true. Our instruments are still crude, our sample size is tiny. But the initial surveys should show hints, whispers of something beyond Earth, and so far mostly silence, which suggests the great filter might come after life begins. Maybe life is easy, but something else is hard. Intelligence, perhaps, or technological civilization, or the ability to avoid self-destruction long enough to become a multi-world species. If life on superhabitable worlds has had tens of billions of years, if it's had time to explore every evolutionary possibility, and yet there's no sign of technological intelligence broadcasting across the stars, then maybe intelligence is the hard part. Maybe it's a rare evolutionary accident, a quirk that doesn't often emerge even given unlimited time and ideal conditions. Or maybe it does emerge, but it doesn't last. Maybe the same stability that favors life, the same lack of climate fluctuation and catastrophic events, also removes the pressures that drive intelligence. Maybe minds only evolve on marginal worlds like Earth, where constant challenges force adaptation, where survival requires cleverness and planning. Maybe we exist because Earth is difficult, not despite it. It's a humbling thought that our struggles, our mass extinctions, our ice ages and impacts and volcanic eruptions, all the disasters that nearly wiped us out, might be the very things that made us possible. And it raises another question. If intelligence is rare or unstable, what about other forms of complexity? What about ecosystems that never develop technology but achieve richness we can't conceive? Worlds alive with biology that fills every niche, that builds structures of extraordinary elegance, that exists in balance for billions of years without ever asking the questions we ask or building the tools we build. Would we even recognize such worlds as significant? Or would we dismiss them as merely inhabited, not intelligent, not interesting beyond their biochemistry? This is a new kind of biocentrism, not the old idea that life is fundamentally different from non-life, that it requires special forces or divine intervention, but the recognition that life shaped by different stars, different planetary conditions, different evolutionary pressures, might not resemble Earth life in its goals or its development. Life under red suns, life in eternal twilight, life that's never known seasons or night or the panic of sudden climate shifts, life that's had 100 billion years to explore chemical space, to build ecosystems of layered complexity, to adapt to environments we find alien and hostile. It wouldn't think like us, wouldn't value what we value, might not even have thoughts in any sense we'd recognize, but it would be alive, and perhaps that's enough. Perhaps the universe doesn't need intelligence. Perhaps the existence of vibrant, complex, evolving ecosystems is itself the point, the natural expression of chemistry given time and energy. And if that's true, then maybe the silence isn't troubling. Maybe it's expected. Maybe the galaxy is full of life that simply doesn't announce itself, because it has no concept of communication across light years, no technology to build transmitters, no curiosity about whether anyone else is out there. Life that exists for its own sake, that thrives in oceans we'll never visit, under skies we'll never see, in chemistries we're only beginning to imagine. Humility before the idea that life need not look like us, nor our home. We've spent so long searching for ourselves reflected in the cosmos, searching for radio signals, for signs of engineering, for evidence of intelligence that thinks the way we think, that builds the way we build. What if we've been asking the wrong questions? What if the galaxy is full of worlds that meet every definition of superhabitable, that harbor life more abundant and ancient than Earth's, but that life has taken paths we never considered, formed structures we wouldn't recognize, achieved states of existence that don't include technology or civilization or any desire to reach beyond their own atmospheres? We might be surrounded by living worlds and never know it. Not because we lack the instruments to detect them, but because we lack the imagination to conceive what we should be looking for. The existential question remains, but perhaps it needs rephrasing. Not where is everyone, but what is everyone? Not why is the galaxy silent, but are we, listening for the right sounds? Not are we alone, but would we recognize company if we found it? These are harder questions, more uncomfortable ones. They don't have simple answers or clear experimental tests. They require us to think beyond anthropocentric assumptions, beyond the idea that intelligence is the pinnacle of evolution, beyond the notion that our kind of consciousness is the only kind that matters. And they point towards something both exciting and daunting. The possibility that the universe is far stranger, far richer, far more alive than we've dared to imagine. But to find those strange, rich, living worlds, we first need to see them clearly. And that requires looking in a new way.